Okay, we're talking about 6-1. Polygons. Very typical geometry lesson, very, very heavy on the vocab. We're just talk about our objectives. We're going to classify polygons by sides and angles. Most of that will be reviewed for most of us. And then we're going to find and use measures of interior and exterior angles. First vocab, they did not give us a spot for, so I snuck it in here. Polygon. It is a closed figure with at least 3 sides. What does it mean to be closed? I have a little picture right here. Closed. Notice the little picture right here that I just drew. This is not closed. It does not close up. There's a little hole right here. There's a little space. That is not a polygon. It must close. Okay, there's that picture. Closed polygon, closed figure with at least 3 sides. Okay, what is the side of a polygon? Pretty straightforward. It's just one of the segments that form a polygon. So here's my little picture. This right here is the side of the polygon. Pretty straightforward. What is the vertex of a polygon? It's the common endpoint of 2 sides. It's a fancy way of saying a corner. Where do 2 of my sides meet? That is a vertex. The plural of vertex is vertices. But vertex, again, fancy way of saying a corner. Diagonal, it's a segment that connects any 2 non-consecutive vertices. So for example, this is a vertex, this is a vertex, this is a side that connects them because they are consecutive. It's one right after the other. A diagonal means I have to go from one vertex to another vertex that are not next to each other. For this vertex to this vertex, that's a diagonal, because I skipped one vertex. I cannot hit 2 consecutive vertices and call that a diagonal. A regular polygon, it is equilateral, which means all the sides are congruent, and it is equiangular, which means all the angles are congruent. So if I tell you I have a regular polygon, I'm telling you that all the sides are congruent and all the angles are congruent. If you need to pause, pause. Keep going. Concave. What does it mean for a polygon to be concave? When part of a diagonal contains points in the exterior of the polygon. I've got a little picture that I can show you. Copy that down. Here's my picture. This is a polygon. Notice it has at least 3 sides and it is closed. There is no little holes, there's no little gaps. But notice what happens. If I try to go from this vertex to this vertex, the diagonal is outside of my shape. It is on the exterior of my shape. So we call that concave. I can do another picture like this. Let's say I have. Again, notice I can go, it looks like I can go from here to there and be okay. All the points are on the inside. But if I try going from here, this vertex to this vertex, it's outside the shape. That's what it means to be concave. And to be convex, it just means that every diagonal that I make lies on the inside of my polygon. For example, this shape right here. If I go from this vertex to this vertex, notice my entire diagonal is inside the polygon. And if I go from this vertex to this vertex, again, the entire diagonal is inside the polygon. That's what it means to be convex. Okay, scroll down. Just write this here for you so you have it available to you. All examples below are both regular and convex. And we just named them for you. You've done this, I think 3rd grade, 4th grade, I forget. You have seen these before. It's got 3 sides, triangle, 4 sides, quadrilateral, 5 sides, pentagon, hexagon, heptagon, octagon, nonagon, 10 sides is decagon, 12 sides is dodecagon, and after we get any bigger than that, we just call it an n-gon. For example, if I have a 16-sided shape, we call it a 16-gon. If I have a 19-sided shape, we call it a 19-gon. Pause it if you need to get all those down, please. When I come up to the 2nd page, do me a favor, write this down on the side of this little chart. that these must be convex. All these shapes, this little pattern I'm going to talk to you about right here, these shapes must be convex for the pattern to hold true. That's what that says. Must be convex for the pattern to hold true. Alright, I got a little picture and everything to hopefully help demonstrate how this works. First one we've talked about, we should know this. Triangle. Triangle is my polygon. Number of sides in the triangle, again, we should know it is 3. Just ask yourself, again, this is kind of funny. I think it'll make more sense here in a little bit. How many triangles do I see in the picture? Obviously, I just see one. And if I add up all the measures of the interior angles, it equals 180 degrees. This, I think, would make more sense here in a little bit. Let me drop down to a quadrilateral. Quadrilateral has 4 sides. Here's a quadrilateral. I have 1, 2, 3, 4. 4 sides. Now, if I draw in a diagonal, notice I create 2 triangles. So within this quadrilateral, I can draw in this diagonal and I create 2 triangles. So the sum of the interior angle measures of a quadrilateral, because I know I have 2 triangles, I can do 2 times 180, so the sum of the angle measures of a quadrilateral has to be 360 degrees. Drop down, pentagon. Pentagon's got 5 sides. Here they are, 1, 2, 3, 4, 5. Notice if I start though at this vertex, and I go to this vertex, and I go to this vertex, I create 3 triangles. So if I have 5 sides, I can create 3 triangles. So if I want to add up the interior angles of a pentagon, it's 3 triangles at 180 degrees each. It's 540 degrees. Hexagon has 6 sides. 1, 2, 3, 4, 5, 6. If I start from a vertex and go to each of the other non-consecutive vertices, I can create 1, 2, 3, 4 triangles. 4 triangles at 180 degrees each means a hexagon, if I add up all the angles, is 720 degrees. Now if we see a pattern here, when I have 3 sides, I have 1 triangle. 4 sides, I have 2 triangles. 5 sides, 3 triangles. 6 sides, 4 triangles. Hopefully you see that the number of triangles is always 2 less than the number of sides. And that's all we're going to say right here. Is that if I have insides, the number of triangles is just that number of sides minus 2. And to get the angle sum, we just take the number of triangles and multiply it times 180 degrees. Just a little bit of practice tells me find the sum of the interior angle measures of a convex heptagon. Well, if it's a heptagon, it has 7 sides. So I must be able to make 5 triangles. So 5 triangles times 180 degrees, 900 degrees of a convex heptagon. Second problem, again, try these on your own first. You'll benefit more if you try it on your own. Find the measure of each interior angle of a regular 16gon. Notice over here they wanted the sum. Now they want to know what each one is. Find the measure of each interior angle of a regular 16gon. If it's a 16gon, it must have 14 triangles. So 14 times 180, so the sum must be 2,520 degrees. But they want to know what each one of them is, not the sum. But if I have a 16gon, I must have 16 angles, and if they are regular, they must all be the same. So I can take 2520 divided by 16, and so each angle must be 157.5 degrees. This next part, I think you'll agree, hopefully it's pretty easy. Write this somewhere on your paper. Flag it. The sum of the exterior angles of a polygon is always 360. So notice if I'm trying to find the sum of the interior, there's this little pattern, this little rule we saw up here. But if you're adding the sum of the exterior angles, it's always 360. It does not change. So I kind of fill this in my little picture here. If this is an equilateral triangle, those are all 60, 60, 60. Linear pairs, which means this exterior angle is 120, that one is 120, that one is 120. If I add up all my exterior angles, it equals 360. Quadrilaterals work the same way. I drew in my picture, I drew in my right angles. Linear pair, these exterior angles must all be 90 as well. If I add up these 4 90s, it gives me 360. They give me this shape. Notice if I add up all my exterior angles, it's always equal to 360 degrees. Those are easy problems. Example, find the sum of the exterior angle measures of a 20-gon. Well, is that going to be any different than finding the sum of the exterior angles of a 50-gon, or a 200-gon, or a 300-gon? No, it's the same. We just said it's 360 degrees. The sum of the exterior angles is always 360. Change it up a little bit. Find the measure of each exterior angle of a regular dodecagon. Well, a dodecagon, if I add up all the exterior angles, it'll be equal to 360. But if I want to know what each one is, and they're regular, if it's a dodecagon, it'll have 12 angles. So 360 divided by 12 is 30 degrees. At the bottom, it just kind of sums it up. We just kind of have a nice little cheat sheet right here to go to. If I'm looking for the sum of the angle measures of the interior angles, I take the number of sides, subtract 2, and multiply by 180 degrees. And if I'm looking for the sum of the angle measures of the exterior angles, it is always 360. Next little piece, if I'm looking for one angle measure of a polygon of a regular shape, I just find the sum, the total. So in the number of sides minus 2 times 180, that gives us the sum, and then just divide by the number of angles that I have. And same thing for the exterior angles. I know that they total 360, so if I want one, just divide by the number of angles that I have. And ignore this bottom piece right here.